So hi everyone, thanks for joining for our webinar series on deep dive on deduplication. My name is Dedup, engineer at DataTorrent. Joining us on webinar is Bhupesh, committer with Apache Apex and software engineer at DataTorrent. Here are some logistics regarding the webinar. This webcast is being recorded. It will be available after the session has ended. To watch again and share with your colleagues who are not able to attend to our session today. The presentation will be available on SlideShare. Please submit your questions throughout the session. You can submit your questions via the question tab in your console, and we'll be happy to answer them as they come up or at the end of session. So without further ado, I'll just hand over to Bhupesh.
Okay, thanks, Deepak. Okay, so we are getting a query that the voice has a little echo. Just let us see if we can reduce that. Okay, great. So hopefully the voice should be better now. Okay. Hello everyone, my name is Bhupesh. I'm a software engineer at DataTorrent and committer at the Apache Apex project. So today's webinar will be on the deep dive on deduplication that is done in Apache Apex and RTS platform from DataTorrent. So here's the agenda for today. We'll start with a brief introduction to Apache Apex first for people or for our users who are listening it for the first time. So we'll just give some introductory slides on Apache Apex. Then we'll jump into deduplication and the related use cases. And then we'll go into a short demo on a simple application that uses deduplication. And then we'll conclude with questions and answers. So you can submit your questions continuously via the questions tab. Our Deepak and Sandeep, our supporters, would be happy to help you, and we can take questions at the end of the session also if required. Okay. So Apache Apex is basically a stream processing platform. It's used for general purpose processing, including stream processing and batch processing. It's just that we call it stream processing since we consider batch as a special case of streaming. It's a Yarn native platform which uses Hadoop Yarn, which is version 2 of Hadoop framework for resource negotiation, and we use HDFS for any persistent storage. It's highly scalable. We can scale statically as well as dynamically. Dynamically meaning we don't have to configure the number of partitions or number of replicas that you want. It can automatically scale based on the incoming load, and also scale down as well to let other applications in the cluster access to the resources as well. It's highly performant. We have seen customer use cases reach single-digit millisecond end-to-end latencies. It's completely fault tolerant. It automatically recovers from failures without any manual intervention. It's also stateful and guarantees that there will be no loss of state. It has all the it supports all the semantics like at least once, at most once, and exactly once. And finally, it's very easily operable, which comes from its very easy to use API and for developing operators and applications. So a little bit of history. The project development started in 2012 at DataTorrent. We open sourced in 2015, and like around 8 months later, we were a top level project in Apache. Okay. So let me go to the platform overview. So at the bottom, you can see the physical, virtual, or cloud infrastructure, based on which you might have any version of Hadoop installed, any flavor. You might have Apache Hadoop, or you may have other major distributions like Cloudera, Hortonworks, Malhar, etc. On top of which you will have Apache Apex engine, which is the streaming runtime. So this particular block, the streaming runtime, takes care of all the scalability and performance and fault tolerance requirements of your applications. On top of which you can see streaming applications running, right? The green blocks, and these green blocks are basically Apex applications, but they may be other applications as well if required. So it can coexist with other yarn applications like MapReduce or any other graph processing application as well. Accompanying these streaming applications, there's a Malhar library, the blue block that you see besides the streaming applications. So this is a library of open source operators. Operators are nothing but reusable business logic that we have kept in the library. So these are very commonly used functionalities that people may usually require to use in their applications. So for example, they may include input-output connectors, like taking reading data from a database, or reading it from some NoSQL store, or even storing data into some, let's say, HDFS or anything like that, right? Including, in addition to these input-output operators, there are various processing operators as well. So deduplication is one of those processing operators that we'll have a look at today. So Malhar allows you to actually use these operators out of the box and without actually writing any piece of code. So it's very highly tested benchmark operators, and users don't have to worry about writing the same functionality again and again. Right? On top of that, there's a DataTorrent enterprise layer where we have all the nice graphical application design and launch utilities. We have visualization dashboards and management consoles and so on. Right? Management console is still a part of the community edition. You can use it for free and see. It allows you basically to monitor an application, view how much resources it is consuming, monitor the latency, the throughput, and those things. Right? We'll have a look in the demo of how a management console looks. And then you have the REST API, which allows you to plug your existing applications into the Apex platform. So coming to an Apex application, it's actually a DAG, which stands for Directed Acyclic Graph. It contains of nodes and edges. The nodes are basically your operators or the business logic, and the edges are the streams which connect one operator to the other. Right? And these edges or the streams are the ones on which the tuples or the records, your data flows. Right? So an operator is responsible for taking the data on an incoming stream, processing it, and sending the processed data out on the outgoing stream. Right? And including all these operators, you can create any directed acyclic graph, and that defines your application. Right? The benefit of the dividing this functionality into various operators is that each of these operators may run independently on a large cluster on independent containers in nodes, right? In different nodes. You don't have to worry about on what node is running which operator or anything like that. Apex takes complete care of it. You're taking advantage of the facilities provided by Yarn. Additionally, each of these operators can be replicated into as many replicas as you want. We call them partitions. So any operator can be partitioned into a lot of different partitions which do the same operation on different sets of data, so that your incoming load is divided into all these partitions, and you can handle a high amount of load and without increasing the latency. Okay. So let's see what Apex as a Yarn application means. So this slide is basically to let you know that how it looks like in a Yarn cluster, right? There are magenta colored blocks you see, which represents MapReduce applications, and you also see green colored blocks, which is nothing but an Apex application. So ignoring the magenta colored blocks, we can see that there are 6 blocks, 6 green colored blocks, each representing one of the operators in the application. You also see a green colored block on the second node called Stram, which is nothing but the streaming application master. It is one of those things that a Yarn application requires for every application to be for every Yarn application. There needs to be a application master provided by that. And so in this case, Apex is basically a Yarn application which has its own application master and which takes care of its own operators. So all these operators you see are connected by dotted lines, and these dotted lines nothing but mean the streams, and the streams mean that the data flows from the upstream operator to the downstream operator. So flows from 1 to 3, 2 to 3, 3 to 4, and so on. You also see 4 and 6 on the same container, which means that they are container local. We have defined a locality between two operators on a stream. You can define them to be a container local. They can be even local to a node. They can be local to a rack, or they can even be local to a thread. So if you want two operators to run on the same thread, that is even possible. So we have all these localities defined, and you can use them in their applications depending on the use cases. Okay. Okay, so let's jump on to deduplication. Okay, deduplication is basically a very common use case. You might have seen a lot of data sets which have duplicates, right? When data passes from a lot of different sources, there tends to be a duplication of data a lot of times. And that is the reason in all the ETL use cases or data ingestion use cases, all the cleansing that is needed in the ETL use cases usually has deduplication before any other processing is done. So on the face of it, it looks like a very basic functionality. As the diagram indicates, you get the initial data to the dedup operator. So dedup is basically short for deduplication. Don't be confused by the nomenclature. So, and it's basically responsible to separate out the duplicate data and the unique data. So if there is any repeating data, it's just separated out into a separate data set called duplicate data, and you pass the original data to other processing units. Okay. Let's look at dedup in a little more detail. So it does not look like a very complicated operation. If you want to write a deduplication logic in some programming language, it's pretty simple. All you need is a hash set, for example, and what you do is when you get a data tuple, you extract the key out of it and store the key in the hash set. Right? At the same time, you also check if the key already exists in the hash set. If it exists, then it's a duplicate of some initial key. Right? If it does not exist, you mark it as a unique tuple and insert the key in the hash set. So all it requires is a hash set and some lookup operations on it, which seem to be pretty straightforward. Right? But the problem is we need to store all the set of keys that we have seen so far. So all the unique keys that come to you need to be stored in that hash set. And the situation becomes even more complicated when the source data is very large, right? Or even when the incoming data is actually a stream, which never ends. Right? So that is what we call stream processing, right? It's a 24/7 365 running application which consumes whatever data it gets. Right? So in those cases, all the incoming unique keys need to be detected and stored. Right? And not only that, you also need to, for any new tuple that comes in, you extract the key, and you also need to look up that key in that existing set of keys. So as your search space increases, you tend to get slow in the application. Right? So any in-memory technique would definitely fail in this scenario and would need more sophisticated techniques. So as there's a quote, right? To duplicate is nature, to dedup is costly. So this is what deduplication actually looks like in a sophisticated scenario. You have a dedup operator indicated by a CN block. There's data flowing from some data set to the dedup operator. It separates the keys into unique and duplicate, and also looks up the data or the keys or the any incoming key. It looks up into a system called managed state. So we'll see what managed state is, but for now, just consider that it's some kind of hash set based on your HDFS, right? So imagine what you could do if your hash set is based on the HDFS, right? Because HDFS is like infinite storage for you, and only problem there is lookups and searching. So that is facilitated by the managed state. So as I said, managed state is a fault-tolerant, large-scale, persistent bucketing mechanism, and it uses HDFS by default. You can plug in any other file system as well. But for now, consider that it's just a bucketing mechanism. As I said, it's a hash set, and you can have different buckets defined there. And whenever an incoming key comes, you know where to look for data in the managed state. right? So you can take the key, you can take the key and look it up into the managed state, and if the key exists in that bucket, then it's a duplicate. If it does not, it's a unique tuple, and you then store the key in the bucket. Right? So basically, it uses a concept of buckets to store the keys onto the storage. Right? And bucket is, just as I explained, it's an abstraction for a collection of tuples, all of which share a common hash value. So for example, you can have a bucket for 5 contiguous minutes, right? If time is a key, you can store data for, let's say, 0 to 5 minutes in the same key, and then 6 to 10 minutes in the same bucket, and so on, right? So you have like concepts like bucket span, which tells you how large a bucket is. So a bucket span in this case of a time-based key can be defined as let's say a minute is a span for a bucket, right? So you have a bucket of width 1 minute, or you can have a bucket of width 1 hour, or anything like that. You can configure it and have a bucket span, and basically all the I/O is done on HDFS, right? So it's pretty slow, as you may imagine. But the problem is the thing that is facilitated by the managed state is that there's an in-memory cache as well, so that repeated access are faster, and there's also facilitation for asynchronous processing, so that all the requests that you make to the managed state, you can have it asynchronous, so that whenever the result is retrieved, the dedup operator can be notified of it, and you can have the result of the deduplication. And meanwhile, you can start processing other tuples as they come. Right? Yeah. So there's also a concept of spillable data structures here, which is basically all your primitive data structures based on managed state. So for a map, for example, you can have a spillable map defined. For an array list, you can have a spillable array list defined, and so on. So a lot of these spillable data structures are also part of the Malhar library. All you have to do is use them as normal data structures, and in the background, managed state takes care of persisting them onto the HDFS, all the caching, all the asynchronicity, and so on. Right? So you don't have to worry about all those details. You can just start using the spillable data structures as you are using any other data structure, any other in-memory data structure. Right? Only difference is these data structures will be persisted, and in case of a failure, you have not lost the data. You still have that data. And it also takes care of all the consistency of your data. So at any time you fail, it goes back to the last consistent state and starts from there, so that the integrity of your data remains constant. Right. So as we discussed earlier, so apart from the managed state descriptions, as we discussed, in-memory techniques definitely fail. So to address those solutions are here. Right? Memory fills up too fast, then you use some persistent storage like HDFS. Search becomes slow. You use some kind of hashing mechanism, and managed state and spillable data structures in case of Apex would do the same thing for you. And even with managed state and spillable data structures, you go on accumulating all the keys that come to you, right? So at over a period of time, you are bound to become pretty slow, and the latency will go up. So in that case, there's a concept called expiry, which is usually used in stream processing scenarios that you will see next. Right? So what is expiry exactly? So before proceeding, let me just remind you all, if you have any questions, maybe you can just put them onto the questions tab on the right hand side. Our supporters, Deepak and Sandeep, will definitely get back to you on that. If not, we will stop at the end of the session and take any questions if pending. So let's go to the concept of expiry. Basically, expiry is what allows you to purge state over time. Right? So usually it takes advantage of the fact that in all the usual scenarios, most practical scenarios, all the duplicates occur within a short time interval or a short span of the original key. Right? So a more common use case is log replay. Right? So what happens in log replay is whenever a machine goes down, you would like to replay the logs so as to send the logs to the master, which might have the machine that went down does not know what keys were sent and what were not. So it does a log replay of all the transactions to the master again. So in that case, there is bound to be a set of duplicates introduced, and deduplication is the perfect example here. But a more suitable example for this is so expiry is a more prominent thing in this particular use case, where you know that within an hour of my log replay, or within an hour of my original record, I'll encounter some duplicates, and not more than an hour apart, right? So you can set an expiry for 1 hour, and you can only store all the data for the past 1 hour in order to do the deduplication for your data. Right? So you don't need to. So if the application is running 365 24/7, you don't need to store the data for the entire year. You just need to store the data for the past 1 hour that is required. Right? And this may be applicable to any time period. It can be even in days or even in months. Right? So you can say I may encounter duplicates within 1 month of receiving my original tuple, and that is fine. You can configure the expiry to be 1 month back, and you will store all the data for 1 month. The thing is that the data that you have to store becomes constant, right? It does not keep increasing over time, and that gives you an advantage in stabilizing your latency. You can define whatever partitioning you want, whatever replication you want, and then at one point your delay or the latency will be stabilized, and you don't have to worry about it anymore. Okay. So currently we support time as a expiry key, since it's a very natural thing to expire on time. Right? So here's an example schema. Let's say we have a tuple or a record which has the following schema. We have the name, phone, email, date, state, zip, and country. Right? So let's say we consider email as the primary key of this schema, and let's say we consider time or the date field here as the expiry key, right? So your email becomes the dedup key, and the time or the date field becomes your expiry key. Now the date here indicates 9th of November 2015 around 1:38 p.m. in the afternoon. Right? So if you keep let's say 1 hour as the expiry period, then all the data that you have to store would be between 12:38 to 1:38 p.m. Right? So you don't have to store all the data that you have got till now. You can just purge the state over time, and a managed state allows for the purging of the state as well. Okay, so let's look at the expiry thing in little detail. So in order to process these things, we have a couple of data points that we keep in the data structures. So we have the latest point of the time, and we have the expiry point, right? And as you can say, and you will also have an expiry period. So in this case, let's say expiry period is say 10, for example, 10 units. You can consider seconds or milliseconds or anything like that. So if it's say, for example, 10 seconds, your expiry point will be calculated as the latest point minus the expiry period. So let's look at the example. So first tuple, when the first tuple comes, your expiry key or the time field, for example, is 10, right? And your latest point becomes 10 in that case, because the latest time that you have seen till now is 10. Right? And the expiry point is 1 in this case, because you have calculated it based on the this particular formula, right? And the significance of expiry point is that at any point of time you get an input tuple, you compare it to the expiry point. If it is less than the expiry point, you can just straight away say that tuple is expired. Okay? So let's look at the second tuple here. It comes with the expiry key 20, and that makes our latest point 20, because 20 is the highest we have seen till now. The expiry point also shifts ahead, making it 11. Right? So anything before 11 is now expired. Same thing goes on for tuple 3 and 4, where your latest is 40 and expiry point is 31. Now let's look at tuple 5. It's a special case. It comes with the expiry key 21, which is far less than what we have seen till now. The latest point does not change; it stays at 40, and even the expiry point does not change. But the moment you get 21, you compare it to the expiry point first. If it is less than that, you decide that this tuple is expired, right? So once the tuple is expired, you just ignore it from any further processing. Okay, so it seems we have a question here. The question is, when we say expiry time, is it a TTL like MongoDB? Okay, so expiry point is, when I say expiry time, it's nothing but the time at which my tuple has, right? So it may be a time field in my tuple. So recently there's a trend in event time processing, right? The trend says that you process the data based on the time that it was generated, not at the time that the application got that data. So maybe the data was generated long back and the application is just getting the data right now. So we cannot process the data based on the time it is getting. We have to process the data at the time the data was generated, and that time is usually there in the time field, in some or the other time field in the data. Right? So your tuple may have a time field or a date field or a timestamp field or anything like that. So that's the expiry key that we are considering here. So coming back on tuple number 5, we consider that this tuple is expired. Going on to the next thing, tuple number 6, we say we have the expiry key is 35. The latest point and expiry point don't change, but in this case the tuple is not expired since it's greater than 31, the expiry point. So we still consider the tuple in processing. So the significance of the last field here, last column, which says decision for the tuple, it basically says that all the non-expired tuples will be taken into consideration for decision of unique or duplicate. Any expired tuples won't even be considered for that processing, right? So once you decide that something is expired, you just move that tuple to further processing and say that okay, we'll see whether this tuple is actually a duplicate or it's a unique tuple. Okay. So let's go to the next slide. Okay, so this is the architecture of the deduplication. So you can see a lot of blocks here. Basically, it's what all we have seen. We have a deduper. The first thing that it does is the tuple arrives at the deduper. The second step the deduper does is check the time boundaries to see if the tuple is expired. If it is expired, we just throw it to the expired port, and the expired port can be consumed by some output operator like say HDFS, and it will just log those expired tuples in some file, right? If it is not expired, the dedup looks up the manage state asynchronously. So it fires up a lookup query on the manage state and says that okay, give me any tell me whether this particular key already exists in the manage state, right? And once it fires that request asynchronously, it just goes back to processing the next tuple. It does not care about when the result comes back, right? So once all these tuples in that particular window are processed, it just checks whether it has received any feedback from the previous query that it had fired, right? If it has received, it will just process that query or process that result saying unique or duplicate, and then look up for the next result. Right? So that is the way it processes. It takes advantage of the asynchronicity provided by the managed state to process all the tuples as soon as they come in, and there is no loss of latency here. So we get a very low latency, and the tuples are processed in time. Right. So just to remind again, managed state is also part of the Apex Malhar project. So you can take a look at it. You can use managed state and all the spillable transactions that come along with it. Okay, so let's go a little bit more into the bucketing system here. So let me just describe what we see in the diagram here. On the first block, you see a lot of blue blocks labeled 0 to 11, right? And then you have bucket indices from 0 to 3, right? So basically the upper part is nothing but your data, right? And these blocks nothing but represent time, for example, in this case. So let's say the 0th block represents time from for 1 hour, for example, say 0 to 1 hour. The first block represents 1 to 2 and so on, right? And the lower one, the 0 to 3 one, is nothing but our storage or the state that we store, right? So let's say we have defined 4 hours as the expiry. So in this case, the length of this array bucket indices will be proportional to the expiry period. Since we have said it will be 4 hours, we have 4 blocks, each of 1 hour, and that 1 hour is nothing but the span of that bucket, right? So one bucket spans an hour. On the top, you can see bucket number 0 to 11. These are nothing but the incoming tuples. So naturally, you will get data from 0, 1, 2, and 3 first. So once this data comes, you just keep on storing them into the bucket indices, right? And this diagram is actually to illustrate how expiry works, right? So once you have filled up the block number 3 in the bucket indices, any new data that you get, let's say from block number 4, will go on to block number 0, and you can say that block number 0 is now expired, right? Which you can see in the lower rectangle. So in the middle rectangle, you can see the block 0 is expired. Block 1, 2, and 3 stay into 1, 2, and 3 in the bucket indices, but block number 0 in the bucket indices is now replaced by block number 4, right? And so it happens that any new thing keeps on replacing the older block, right? It's like a least recently used replacement, right? So in this, not exactly a least recently used, but the least recent block is replaced. So it may happen that you may have used block number 0 the last time, but since you're getting data from block number 4 now, which means that your latest point has shifted and you must expire the very old block number 0. Okay? So this is how expiry takes place. Okay, so here's what we have in the Malhar library right now. We have options for deduplication of bounded data or deduplication of unbounded data. So whenever unbounded data comes in, it's basically a streaming scenario, right? And we have all the facilities for expiry and all those things for unbounded data sets. For bounded data sets, which is nothing but a batch scenario, right? A lot of cases where you need to deduplicate a file, right? Deduplicate in a set of file, you need to find, say, for example, all the unique customer IDs, for example. So this does not require any expiry-like concept, and you don't care about the latency so much. You just care about the throughput. So you just process the data without any concept of expiry, and you can just use the managed state for that. And there's a bounded data deduplication for that. All you need to specify for that is the key for deduplication, like customer ID in this case. For unbounded data, there are other fields that you need to specify. The key for deduplication is one. The time field for expiry is another, which tells you what time the data was generated. And then there's the expiry duration, which is like last 1 hour or last 4 hours or last 3 months or something like that. Right? You also need to specify the reference time. So you also can consider since when you want to consider the expiry, since the beginning of time or since right now or so on, right? And then you have the bucket span, which specifies how large you want a bucket. So the bucket span is basically a performance optimization kind of configuration. You can play with different bucket spans to see what gives you best performance. Okay. So let's look at a simple demo. So we have a simple application running here, which is basically a ETL application. So let me just show the directed acyclic graph related to that, right? So this screen shows the directed acyclic graph, the DAG. It starts with an operator called Kafka, which is nothing but input operator, a Kafka input operator, which reads data from Kafka, right? We have another application running parallelly, which is actually continuously pushing data into the Kafka, and that is the reason you see that there are like around 2,000 records being processed per second, right? The Kafka sends the data to the parser, which parses the data. So the data is basically CSV data. It parses the data using the separator and creates a POJO out of it, right? A Java object out of it. The Java object is then passed on to the deduplication operator, which takes care of all the functionality that we just talked about. Right? The deduplicates and the expired outputs are thrown on the respective ports. There are also an error port to specify whether any tuple is an error tuple or something like that. And then you have all the unique tuples going on to the transform operator. Right? The transform will transform the data in some fashion, maybe look up some database to populate some additional fields in the object and pass on the transformed object to the formatter. Formatter will actually format it in a nice fashion so that it can be viewed by the user and writes it down to the HDFS output operator. The HDFS output operator actually writes it down to HDFS. So this is nothing but a logical DAG, right? The logical DAG that you have defined in an application. Basically, all you do is define these operators. A lot of these operators are already available in Malhar. So in fact, in this case, all of these are available in Malhar. You can just pick up those operators, stitch them using the API provided by Apex, and then you get a DAG and you start the application. Right? However, what happens at runtime is the physical plan gets into picture, right? So the logical plan is what you define. The physical is what is actually executed. So what actually executes is with all the replication and the partitioning that you have defined. So in this case, it happens that we are pushing data into two different topics in Kafka, right? Let's say CDR0 and CDR1. So if you look at the physical tag view, you will actually see two different Kafka operators, which are reading data from the two different topics. Right? And they were supposed to send data to the parser. But in this case, the system or the engine actually inserts another operator called unifier into the system so that both these streams can be unified and a single stream can go to the parser operator. Right? Similarly, so the Kafka operator, we had not defined how much to partition. It automatically partitioned it based on how many topics were available in Kafka to read. Right? So we can define what topics to read, and it will partition it itself automatically. Whereas for the dedup operator, what we do is we can specify a static time partitioning. We have defined a partitioning of 2 for this. Since the parser operator is a pretty fast operator than the dedup operator, we have multiple instances of dedup operator to handle the same amount of load that the parser can handle. Right? And then you can see for all the output ports of the dedup operator, there are unifiers inserted by the platform which go to the respective operators downstream. Right? And then you can see the transform, formatter, and HDFS output as was in the logical plan, because we have not defined any partitioning for them. Right? So this is your application running at a high scale. So you can see on the top. So this particular screen is the management console, right? This is free to use. You can. It's part of the community edition. You can download it and use it for free. This allows you to monitor your application continuously. So if you go to the physical tab here, it shows what all operators are running and what are the container IDs for those operators. So these container IDs are actually recognized by Yarn, and you can see the actual container ID related to that, right? So on the screen, on the next screen, that I just clicked on a container, and it showed me a number called container underscore something something, right? It's an actual Yarn container ID. Right? It also tells you the host on which it is running and the JVM on which it is running. It tells you how much memory is allocated to this particular container, when was the last heartbeat, how many operators are there in that container, and so on. When what is started, what is the state, and so on. Right? So all these things you can monitor from the console. Apart from the console container itself, you can also view the application level statistics or the operator level statistics. So in this case, the application state is running, what is the current window ID that is in process, what is the recovery window ID, which is nothing but what state it will go back to if there is any failure. You can see the latency, how many tuples are processed, emitted per second, total processed, total emitted, how many operators are there in this DAG as a physical part of it. How many containers were planned and how many were allocated, how much is the total allocated memory. You can see 25 GB is the actual allocation to this application, and various other statistics, right? So this is what the deduplication, so this is just a small example of how the deduplication operator can be used in an application, right? So, okay, so seems like there's a question. So the question is, how will we solve the append functionality of Dedup? So what happens in managed state is basically it creates different files for different windows, right? So and later on at some consistent point it merges them. So it does not actually rely on the append functionality. It just writes the machines down and then writes the data down on the file and then considers them later and merges the data in multiple files. So moving on, let's conclude. Deduplication is basically what we saw as important and complex functionality as far as actual streaming scenarios go, and it's provided out of the box in Apex Malhar and also DataTorrent RTS, which bundles Apex Malhar. You can it uses managed state for state management of very large data and any asynchronous processing that needs to be done to maintain a very low latency. And it uses expiry based semantics for deduplication, streaming based deduplication scenarios. So just to remind you again, Apex Malhar is basically a library, and Apex Core, which is the engine, are the two sub projects of Apache Apex, right? So there's an engine and there's a library to be used along with it. So I think I'm done from my side. There are some resources. You can view the slides and the recorded video of this particular webinar on the DataTorrent channel on YouTube. The slides will be uploaded to SlideShare. And here are some resources. You can maybe subscribe to the forums in Apache DataTorrent. Follow us on Twitter. There are a lot of links on webinars. We do have frequent webinars. We have meetups. And as I said, right, videos and slides and so on. So you can just have a look at these and drop any email, drop an email to us on the dev mailing list or even our personal mailing list on DT.